Welcome to our exploration of the biomechanics of human bone, focusing on how bone fixation devices like plates and screws support healing. In this video, we'll break down the principles behind these devices, the types available, and how they're used in clinical practice. Whether you're a student, a healthcare professional, or just curious about how our bodies heal after fractures, you'll find valuable insights here. Let's start by understanding why stable fixation is so crucial for bone healing and how modern technology has revolutionized orthopedic care. Cortical bone fixation is all about stability and compression. Screws and plates are used to provide compression at the fracture site, which promotes bone healing and remodeling. Stable fixation is essential because it minimizes micromotion, allowing the bone to unite properly. Compression not only enhances healing but also encourages the bone to remodel itself, adapting to the mechanical environment. This principle underpins most modern orthopedic fixation techniques, ensuring that fractures heal efficiently and with minimal complications. In designing implants for bone fixation, several biomechanical factors must be considered. Implants need to withstand high loads and stresses, especially in weight-bearing bones. The materials used should be biocompatible to avoid rejection and corrosion-resistant to ensure longevity. Additionally, implant design should minimize stress shielding, a phenomenon where the implant takes on too much load, causing the bone to weaken over time. These considerations are critical for successful long-term outcomes in orthopedic surgery. There are several types of cortical bone plates, each designed for specific clinical scenarios. Locking compression plates (LCP) provide stable fixation and are especially useful in osteoporotic bone. Dynamic compression plates (DCP) allow controlled compression at the fracture site, promoting healing. Limited contact dynamic compression plates (LCDCP) reduce plate-to-bone contact, minimizing stress shielding and improving blood supply. Each plate type is chosen based on the fracture location and the required stability. Locking compression plates, or LCPs, are a breakthrough in bone fixation technology. These plates allow screws to lock into the plate, providing angular stability. This feature is particularly beneficial in osteoporotic bone, where traditional screws might loosen. LCPs are commonly used in diaphyseal fractures of long bones, offering both stability and compression. Their design helps prevent screw loosening and supports bone healing even in challenging cases. Dynamic compression plates, or DCPs, are designed to allow controlled compression at the fracture site. The oval screw holes enable axial compression, which is essential for promoting bone healing. DCPs are suitable for fractures that require less rigid fixation and are commonly used in diaphyseal fractures. Their design supports the natural healing process by providing the right amount of movement and stability. Limited contact dynamic compression plates, or LCDCPs, are designed to reduce the contact area between the plate and the bone. This minimizes stress shielding and improves the periosteal blood supply, which is crucial for bone healing. LCDCPs are often used in fractures that require less rigid fixation, allowing the bone to heal more naturally while still providing necessary support. Cortical bone screws come in several varieties, each tailored for specific purposes. Fully threaded screws have threads along their entire length, providing strong compression between the plate and bone. Partially threaded screws are used for lag screw fixation, compressing fracture fragments together. Self-tapping screws have cutting flutes at the tip, eliminating the need for pre-tapping and simplifying the surgical procedure. The choice of screw depends on the fracture type and the desired fixation. Several major companies lead the market in bone fixation technology. Since DePuy Synthes is renowned for its high-quality materials and innovative designs, offering a comprehensive range of plates and screws. Stryker provides a wide array of orthopedic solutions, focusing on minimally invasive techniques. Zimmer Biomet emphasizes patient-specific solutions and advanced bone healing technologies. These companies set the standard for safety, reliability, and innovation in orthopedic implant. Let's look at some specific product examples. Synthes offers LCP compact hand plates and small fragment DCP, which are widely used for various fracture types. Stryker's Vari-Ax locking plates and universal small fragment set provide versatile options for surgeons. Zimmer Biomet CLS plates and periarticular locking plates are designed for stability and precise fit. These products represent the cutting edge of bone fixation technology, ensuring optimal outcomes for patients. When it comes to screws, Synthes provides Cortex screws and self-tapping screws, known for their reliability and ease of use. Stryker offers Cortex screws and self-drilling screws, which simplify the surgical process. Zimmer Biomet's titanium alloy screws and compression screws are designed for strength and durability. Each of these products is engineered to provide optimal fixation and promote bone healing. Fixation in trabecular bone presents unique challenges. Locking compression plates (LCP) offer stable fixation even in the less dense trabecular bone. Cannulated screws allow for precise placement with minimal bone disruption, which is essential for preserving bone integrity. Polyaxial locking plates enable multidirectional screw insertion, providing flexibility in complex fractures. Companies like DePuy Synthes, Stryker, and Zimmer Biomet lead the way in developing these advanced solutions. Specific products for trabecular bone fixation include DePuy's LCP, Stryker's variable angle locking plates, and Zimmer's periarticular locking plates. These products are designed to address the unique needs of trabecular bone, offering stability, flexibility, and minimal disruption. Their advanced engineering ensures that even complex fractures can be managed effectively, supporting rapid and reliable healing. Cortical and cancellous screws are designed for different types of bone. Cortical screws are used in dense, hard bone, while cancellous screws are for spongy, low-density bone. The differences in thread design and core diameter are tailored to maximize fixation and minimize the risk of screw pullout. Understanding these differences is crucial for selecting the right hardware for each clinical situation. Thread design of screws plays a vital role in their function. Cortical screws have fine threads with a small pitch, designed to engage dense cortical bone and provide strong fixation. In contrast, cancellous screws have coarse threads with a large pitch, ideal for gripping spongy cancellous bone. This design ensures that each screw type offers the best possible purchase and stability in its intended environment. Core diameter of screws is another important distinction. Cortical screws have a smaller core diameter, maximizing thread engagement in dense bone and providing greater holding power. Cancellous screws, on the other hand, have a larger core diameter to distribute load over a wider area, preventing pullout in low-density bone. These design features are essential for ensuring secure fixation and successful healing. Cortical screws are primarily used in diaphyseal fractures, plate fixation, and rigid constructs. Their fine threads and small core diameter provide stable fixation in long bones, enhancing compression and promoting healing. These screws are essential for situations where strong, stable fixation is required, such as in weight-bearing bones or complex fractures. Cancellous screws are used in metaphyseal fractures, joint fusions, and osteoporotic bone. Their coarse threads and larger core diameter provide excellent purchase in low-density bone, making them ideal for non-load-bearing applications. These screws are crucial for achieving fixation in areas where traditional cortical screws might not hold as effectively. Summarize: cortical and cancellous screws differ in thread design, core diameter, and clinical application. Cortical screws are best for dense bone and rigid fixation, while cancellous screws excel in spongy bone and non-load-bearing scenarios. Understanding these differences helps surgeons choose the right hardware for each patient, ensuring the best possible outcomes. Advancements in bone fixation technology continue to improve patient outcomes. Modern plates and screws are designed with biocompatible materials, innovative locking mechanisms, and minimally invasive techniques. These innovations reduce complications, speed up recovery, and provide more reliable fixation. As research progresses, we can expect even more effective solutions for bone healing in the future. Conclusion: the biomechanics of bone fixation is a fascinating and rapidly evolving field. Understanding the principles behind plates and screws, their types, and their clinical applications is essential for anyone involved in orthopedic care. With ongoing innovation from leading companies and advances in material science, the future of bone healing looks brighter than ever. Thank you for joining us on this journey through the world of bone fixation. Stay curious and keep learning.